Welcome to Quick Soil Mechanics Lessons with Brian. Continuing liquefaction simply explained in 12 acts. Today, Act 7, flow liquefaction and K-naught consolidation. So what is K-naught? Well, K-naught is the earth pressure at rest. It corresponds to the condition of zero lateral strain. So an odometer or consolidometer is a K-naught test. Has rigid sidewalls, so it can't have lateral strain, but you can load it vertically. K-naught is represented by this ratio of horizontal to vertical stress, and it's also equal to 1 minus sine phi. So let's look at our axes: normal stress, shear stress. I've shown the angle of our friction angle on there. We've got a mock-up of a triaxial shear test sample with orientation of the stresses, and we have a point at the origin. So this sample has not yet been consolidated, but we are going to consolidate it under isotropic consolidation. That means sigma 1 and sigma 3 are equal. We don't have to consolidate it that way. Alternatively, we can consolidate it along a different path. And in this case, we're using K-naught consolidation. Remember those ratios that came up on this line, which is defined by the angle 1 minus sine phi. So let's just get back to our stress paths in MIT space. I've got both friction angles total and effective stress friction angles, and we're going to consolidate that sample and start shearing it. Here's the total stress, effective stress. We build up that the circles as we shear the sample until we hit the failure envelope in total stress and the corresponding effective stress failure circle. We can connect the top of those circles in MIT space with a straight line. In effective stress, we can connect the top of the circles with a line that's defined by those circles, the top of those circles, and those are stress paths in total and effective stress under the MIT convention. So getting back to static or flow liquefaction, we have these images of the facilities in Brazil that failed. Left-hand side, top and bottom is Samarco before and after failure. Right-hand side is Brumadinho before and after failure. So these failures can be just completely catastrophic and devastating. So we need to understand that really well. So here we have our two stress spaces. On the left-hand side, we have stress strain space. Right-hand side, we have stress path space as defined by our MIT method. Now, let's put a specimen that failed under brittle conditions here. This is what we're talking about with static or flow liquefaction, is a brittle failure. So it rises to a peak at low strain levels and rapidly drops off to a post-peak or large strain or ultimate strength. Residual strength comes by various different names. But in stress path space, we have a matching curve. So it rises up to a peak and drops off rapidly to its residual strength. So we've seen that one before. The peaks of those lines pass through a line called the yield surface or collapse surface. It has a few different names. It means the same thing. Now we can also have a condition where we're not starting at the origin, like we showed on an earlier consolidation path. We don't have to be on the x-axis if it's K-naught consolidated, or if there's static shear, like there might be on the outside slope of a dam. So we're not starting at the origin. We have some condition where the point is elevated off of the horizontal axis anyway. So now the dangerous thing is we don't have to go through the peak in order to go through that collapse surface and to end up at the residual strength. So we can go through the stress paths that are shown in the blue line or also the red line. Now the original line in there is static or constant rate of loading. The blue line could be caused by creep, very slow long-term creep, or a condition called constant Q, which might be rising groundwater conditions. So this is under completely drained conditions, but the pore pressure is increasing. Or, as shown in the red lines, we can have cyclic or seismic loading that can get us through that collapse surface without ever going through the peak. So here's the important part to remember when you're analyzing this type of brittle behavior. You don't have to go through the peak. It's actually very dangerous to use either the friction angle or the angle of the collapse surface for slope stability. You would always want to use the residual strength if the static shear on that soil element exceeds the residual strength. So that's very important to remember. Always use that residual strength. Now, a lot of times you don't see this kind of stress path in a triaxial shear test, and that's because it's really hard to pair it loose enough in the lab. But if you run a field vane shear test, a lot of times you can see this type of a behavior. But just because we can't make it loose enough in the lab doesn't mean that it can exist that loose in the field. So very important to remember. Well, I think that is plenty for today. Let's call it quits there, and I will see you back for Act 8.